Hello, my name is Andy Lazur. I'm a water quality specialist with the University of Maryland Extension, and I am going to present information about salty roads and what that means to our drinking water quality. So if we look at salt use, which has progressively and exponentially increased since the 1940s, you can see that the bulk of salt used in the United States is for road salts, for de-icing purposes. And approximately 30 million tons of salt are applied annually in the United States. And of course, obviously that's mostly in the northern states, but it does have a significant impact. And I'm going to share with you today some of the impacts, particularly on drinking water quality, groundwater quality, and the impact that has on public health. It's applied to roads via state agencies, county agencies, and then also private applicators. And we've seen a fair amount of reduction in salt use by state agencies and some counties as well. The use of brine solution, for example, the use of some alternatives, but salt tends to be the most widely used because it's the lowest cost. But again, there are serious issues with excessive use of salt being used, again, both on roads, but also particularly in private applications, parking lots, sidewalks, etc. And this is having an impact both on our stream and surface water quality as well as groundwater. And so this is a little dated chart, but it shows just the increase in salinity or chloride levels in streams. And this darker blue line is the most recent, albeit going on 20 years old now. You can see already at that time, levels were exceeding the EPA secondary maximum contaminant level of 230 parts per million. So numerous streams, and those values have gone even higher, obviously, since then. But most of that activity tends to happen in urban settings or suburban settings. And primarily that's because of the density of roads, for example, and how much salt is being applied. So an important point to note when we talk about surface water quality, stream quality, and groundwater is what the term called connectivity. Our streams and our groundwater are connected. So in the Maryland area, the Piedmont area, more than half of our stream flow is coming from groundwater. So when we are contaminating surface water, we are also impacting our groundwater, and that is the case with road salt application as well. So here's some data from the Maryland Geological Survey. It's just showing you the highest chloride values tend to be concentrated in Maryland around high density areas. And that's where there's a lot of roads and therefore a lot of salt application in the winter months. And the challenging thing about Maryland's weather and climate is that we have frequent storms, frequent melting events, and then more storms. So there has to be numerous applications, whereas in more northern climates, it may be applied once and then there's a permanent kind of a snow cover. But with Maryland, we have this multiple ice storms, snowstorm events, and then melting, and then another event. And so it requires more salt application. And this is some data, again, from the Maryland Geological Survey showing that in groundwater, these are wells, and groundwater has followed that same trend as in surface water chloride content. And that here is, again, chloride concentration in wells exceeding. We've actually seen some private wells in the several thousand milligrams per liter or parts per million in chloride. And that obviously is creating not only a drinking water situation well below that threshold, but also corrosive water, which we'll talk about more, and then also destruction of appliances, things like that. The need to either dig a new well, perhaps deeper, different aquifer perhaps, or different fractured rock structure, or having to install a whole house reverse osmosis system, for example, that could cost tens of thousands of dollars, depending upon the size. So it obviously is having a significant impact. And again, here's a summary of those multitude of impacts. Certainly, salt is increasing the chloride and sodium levels in ground and surface waters. There's literally miles and miles of streams that are impacted. Increased chloride levels is actually affecting the life, the fauna within streams, particularly some invertebrates, and those populations have crashed, and that impacts the whole ecosystem. There's also mobilization of certain bases, minerals, for example. We have the corrosion aspect that I'll talk about. Also, we have mobilization of heavy metals and radionuclides. And obviously, these things increase the risk to public health. Or the declines is in soil pH, aquatic species diversity, permeability, and obviously it's having a negative impact on drinking water quality. I'm going to cover a couple of things, particularly the risks to public health as we see impairment to drinking water quality. We've probably all heard of the Flint, Michigan lead toxicity crisis. And this was a result of several factors, not only a change in the water source, but then also a change in the treatment. So what happened is when they changed the source, there was increased chloride levels. There was not a application of a corrosion inhibitor. And what happened is that allowed the increased corrosivity of the water to actually leach lead and other metals from the plumbing, particularly older plumbing, whether it be lead pipe or leaded fixtures. Fixtures dating before 1984 had a higher percentage of lead, whether it's brass fittings, whether it's a faucet fitting, etc. So there's been numerous situations with lead toxicity. The Flint, Michigan crisis is just one. DC had one back in the early 2000s, but many other municipalities have had similar types of instances, and obviously it's impacting public health. The other thing is that groundwater quality is a reflection of the geology, and it makes sense. So if water is in contact with soil or rock or minerals, it's going to take up some of those minerals or other contaminants. And in this case, in much of the mid-Atlantic region, and this graph shows that there's actually along the East Coast, there are numerous states that have a high prevalence of corrosivity of their groundwater. So when we look at lead, lead is an issue because you don't know if you have lead or not. And the only way to know is by testing because it's colorless and odorless. Okay, now you may see some signs as in these photos here where because of corrosive water, not because of the lead, but because of corrosive water, you're getting pitting on some of your plumbing fixtures, or you may even see this bluish green stain. That's an indication of corrosive water leaching out copper from the plumbing, whether it be copper pipe, whether it be fittings, whether it be actual fixtures that have copper and lead in it. So the lead is not in the groundwater, but it's, again, coming from the plumbing due to corrosive water. And corrosive water is caused by several things. Could be a low pH in combination with very low, what's called bases, carbonate bases, but also with elevated chloride. So again, they've come up with this chloride to sulfate ratio, and anything over 0.5 or half is considered corrosive water. And sulfate, interestingly, actually inhibits corrosion by forming a protective film layer, okay? And chlorides actually, again, destroy that ability to form layers. So what happened in Flint is because due to the changes, the CSMR went from less than half to 2.0. And obviously that created a lot of lead leaching from the water, and then that created the human toxicity situations that were observed. Now, interestingly, also, a study in Virginia showed that 89% of the wells, these are private wells, had a CSMR of greater than 0.5, which means, again, that water tends to be on the corrosive side. And if there is lead present in that plumbing, they would be at increased risk of exposure to lead. Okay, this corrosion is very expensive. Obviously, putting salt on the roads, you can see the damage to bridge infrastructure, whether it be the concrete or the metal railing, certainly to damage to cars. But what's interestingly, studies have shown that the damage to private home plumbing is actually twice as much damage to public water supply systems as well. Again, think about it. You have corrosive water, your water heaters, your dishwashers, even your plumbing. For example, copper pipes sometimes have pinhole leaks because of corrosive water. So again, a lot of damage to plumbing due to corrosivity. And this is another diagram that shows how this works. So the upper diagram is a situation where you have lead pipe and you have galvanized pipe, but with a corrosion inhibitor in a treatment system, from a municipal treatment system, in this case a phosphate, it's actually coating the lead pipe, and therefore the water is not chipping away or eroding away at the scale, the leaded scale. Now, the bottom graph is showing that without these corrosion inhibitors, what happens is that this scale, this corrosive water, is kind of chipping off some of this scale and some of the lead and zinc, cadmium, copper that's in that scale, and that's being dissolved into the water, and then that's consumed. So again, that's the reason for lead toxicity and other heavy metal toxicity in home plumbing. It's because of the corrosiveness of water eroding away at the metals in the actual fixtures and in the scale that has formed. That's kind of normally would protect from metal leaching. So what we've seen with this CSMR ratio is that in urban settings where we have a higher density of road and road salt use, we tend to have elevated CSMR ratios, and therefore we have increased corrosion. And in some cases, it can get pretty high to where it's very difficult to control. So adding on to metal mobilization, in addition to lead, we have other metals that can be mobilized. In other words, typically they may normally be bound in, say, certain sediments or fractions of the sediments and soils. The increased sodium and chloride actually moves that metal into the groundwater. Cadmium obviously is, and chromium, copper, iron, nickel, and lead, and zinc. These metals can be toxic at certain concentrations. And again, it's due to several factors here, but again, the important point to realize is that the impact that chloride and sodium is having on our soils and on our groundwater. What's interesting is certain soils are more prone. So if you have a high organic matter concentration in your soils, you tend to have less metal mobilization or leaching. Again, these metals, as I mentioned, they're toxic. They create a multitude of issues with human health, liver, skin, kidneys, brain. Again, these are just some specifics here: arsenic, cadmium, chromium. You can see that the issues that can occur: kidney damage, skin issues, liver issues. Now, in addition to heavy metal mobilization, there's also radionuclides. The more common ones you may be familiar with are radium and radon. We're familiar with radon because oftentimes we might have our homes tested for radon gas if we're selling our home, for example. But radon can occur in rock and soils. So what happens is that with increased chloride within the soils, you actually can mobilize some of these radionuclides, radium and radon in particular, and that can move through into these elements rather are releasing these particles that are toxic. And again, that includes, kidney damage, lung damage, and cancer. So what's interesting is looking at some of the studies that have been done, specifically here in Maryland, showed that groundwaters that had concentrations of sodium and chloride greater than 10 and 15 milligrams per liter had levels of radium exceeding the EPA maximum contaminant level. Then again, another study, particularly in certain aquifers in a certain part of the state, also showed that 60 out of 122, about almost half of the wells tested showed concentrations of radium above the EPA limit. Now, chloride's the issue, but also sodium. Again, this is also creating some issues with our soils and mobilization. This actually shows a positive correlation between the concentration of sodium here on the x-axis and the concentration of radium on the y-axis here. And again, this is the EPA threshold right here. And you can see that as sodium increases, then the level or concentration of radium is observed to be high as well. So what can we do? What can we do as homeowners? Certainly we need to be aware. We need to be aware of what's going on in our county and our state. What are our counties and state doing to reduce use? The challenge with chloride in particular is that it's highly mobile. It pretty much goes straight through the soil into groundwater. So there's very little remediation. There's been numerous studies trying to show, can you bind it up with different types of, wetlands and buffers and things like that. And you get a slight amount of, remediation or binding of chloride within organic matter. But again, constant use, yearly use of salt just basically leads to accumulation of chloride within the soil. And then it leaches through, goes into the streams, goes into the groundwater. And so there's very little that we can do. So the best strategy has been reduction. And in some states, I know Maryland has seen about a 50% or even greater than 50% reduction in salt use. And that is due to a number of practices, including what's called a snow college, training their employees and contractors on how to track use, different types of application methods. The anti-icing, the brine, for example, is just one example. So there's been some significant progress there, and some of the counties have adopted those same practices. But again, there's still a lot of situations where excessive salt is used. So a homeowner can be aware. So other tips, particularly at your home, what can you do? And one of the things is to shovel snow before it accumulates. Once snow accumulates, it's very difficult to de-ice it. So it's best to stay on top of the storm. If you're unable to shovel, consider hiring somebody that can come. Depending upon the storm and the severity of the storm, they may have to come 2 or 3 times during that storm, so it doesn't layer. It doesn't, you don't have a deep layer, because at that point there's really nothing that you can do with salt. You'd just be, it wouldn't be effective in reducing that. You have to get down to as close to the sidewalk as possible. The other thing that you can do is actually consider covering your steps, for example. If that's the area that presents the greatest slip hazard, is covering it with a tarp before the storm and then removing it right after the storm. And that way you have clean steps, and you have reduced the need for salt as well as reduced the slip hazard. You can also use sand. Sand has worked well. And in fact, decades ago, sand was used a lot more than salt is, but that's not the case today. Because sand has an issue as well, because again, depending upon the quality of the sand, source of sand, it may have a lot of clay particles in it. So if you're adding this type of material, you're adding a lot of organic matter or silt that could negatively impact waterways. Okay, there are alternatives. And EPA has a nice site there called Safer Choice Products. And this includes a multitude of home products, not just salting, but cleaning, things like that. Calcium magnesium acetate is, again, one example. And those tend to work best when temperatures are not extreme, when they're above 25. So again, there are some options, but you need to follow those directions and only use a de-icer, whether it be salt or CMA or whatever the case may be. Only use it on the areas that are the most important. Whether that be your steps, sidewalk, whatever the case may be, where there's the greatest slip hazard. And again, follow the label. Again, the idea that, well, if a little works, more work will work a lot better. And that's certainly not the case. And then you also have to consider that salt in particular can kill plants, for example, and can impact your vehicles, things like that. But the biggest thing that we're concerned about is groundwater quality. So just to kind of review the implications of road salts and on-ground and drinking water quality, I shared with you numerous negative impacts as a result. And again, one of the things that occurs with increasing chloride is increasing water corrosivity, which can create toxic metal leaching from plumbing. But then there's also heavy metal and radionuclide mobilization within soils to groundwater due to elevated chloride and elevated sodium. So as a result of that, private water is not tested as it is with municipal water. EPA regulates all public waters. The states then are mandated to follow at least what the EPA requires, and there's roughly 95 some odd contaminants that public water is tested for, including chloride and sulfate metals and things like that. And then if they're there, they exist, then they're treated. Whereas private wells, it's the responsibility of the homeowner or the owner, the well owner, to test. And unfortunately, most well owners in the United States do not test their water as they should be. So one of the recommendations with increasing chlorides, cumulative chloride levels, impacts on groundwater, is to start testing for both chloride and sulfate and metals and radionuclides in private wells. Again, these test results can guide treatment decisions, and that's really important to do. And again, just the previous slide presents some homeowner salt stewardship practices. I encourage you to follow those. So here's a list of a few resources, a wealth of information on road salts, the impact to both streams and our groundwater quality. And thank you.